class. So in the last class, we have covered the transmission lines full concept. Then today we'll start with the waveguides. Yeah, you can ask the question.
No, sir, I was just checking. My audio was not working.
So now we'll start with the waveguides. So basically this chapter is very easy if you see the gate problems and that. But actually the thing is here you need to understand the basic concept, because even if you go for higher studies and if you want to do your MTech in high power microwaves, or if you want to choose your domain in electromagnetic theory future, it requires you need to understand the complete basics of the waveguide theory and all. But as per the exam point is concerned, in this chapter there are a lot of derivations will be there. I mean, we are going to discuss about the different kind of waves, transverse electric, transverse magnetic. So all those Maxwell's equations you have to solve all these things and are required. But as per the gate point is concerned, the full problems can be easily solved with 4 to 5 problems that can be put in a different configurations, I can say. But here at some points I can give an approach. At least I will not go through the complete derivation part, but just I will tell you the approach and how to follow that, because at this moment you are preparing for the gate. By keeping that point in my mind, I was confining at some places. I will tell you the approach how to do that. But as per the problems are concerned, it is very, very simple. Okay. And of course, you would have been also seen in your academics when you see the waveguide theory, you have to start with the wave equations and you have to derive all those equations and find out what is the solution for electric field and magnetic field. So that is a conventional way of doing it. But I will tell you a simple shortcut at some of the places how to arrive at those solutions. So when you start with the waveguides are basically chosen for energy propagation in the form of electric field and magnetic field at gigahertz frequencies. The question arises why the waveguides cannot be designed at low frequencies, right? And suppose if you want to design a low frequency in the frequency range of some 100 megahertz, let us say. So or you can say 100 kilohertz. Typically, I will give an example. The dimension of the waveguide is closely related to the wavelength at which you are operating. So suppose when you are talking about 300 kilohertz and your wavelength is going to come around approximately 3 into 10 power 5, you are going to get 1 kilometer. So you cannot design a waveguide with a dimension which is equal to in the range of kilometers. So later in our discussion, you can see how the waveguide dimensions are related to the frequency of operation. So as of now, we can remember that the dimension of the waveguide is purely a function of the frequency. So when you go for the gigahertz frequency, your dimension is going to come in the order of centimeters. So you can easily design the waveguides. Okay, so that is the reason why the main purpose of the waveguides will be for the energy propagation at gigahertz range, and the energy is also propagated in the form of electric field and magnetic field using your total internal reflection. So that is the basic mechanism how the wave is going to propagate. So here I already mentioned some of the introduction here. So these are all basically applicable at gigahertz range. And at the same time, what will happen suppose if you don't have any waveguide and I have a high power microwave transmitter? Okay, that is going to I cannot transmit the electromagnetic wave just by using an amplifier. So what will happen if you go to the communication? There is a power amplifier. and there is an antenna. So the antenna is going to radiate the electromagnetic fields. So what will happen? This power amplifier is going to create the electromagnetic radiation. And if you want to connect this amplifier output to the antenna input, you require a transmission line. And when you are talking about gigahertz range, the waveguide can be considered as a transmission line. So in order to feed a power at gigahertz range frequencies to the antenna, you need a waveguide to be connected between your power amplifier and your antenna module. So this waveguide is basically act like a guided structure so that the power density will be maintained uniform. So what actually, suppose if you don't have any waveguide was, as you can see here, assume that this is my axis of the wave propagation. This is what actually my intended direction. But in our elementary physics we have studied, as the distance progresses, the wave is trying to expand out. Okay. These are all called your spherical wave fronts. The distance increases, what is the nature of the electromagnetic wave? We are assuming that the wave is uniformly propagating without any expansion. But that is not the case. So as the distance progresses, the wave is trying to expand out like this. So to put it in a simple word, let us assume that the source is going to deliver a power of 100 watts. When you are very near to the source, the 100 watt is going to distribute over a small area. And as the distance progresses, the full 100 watt is going to distribute over a larger area. As a result, what will happen? Let me consider a small area here and let me consider a small area here. I'm assuming that the area of this one and the area of this one is same. Can you tell me in which case the power available will be more if you consider the same area? Is it when you are near to the source or when you are far from the source? Correct. So when you are very near to the source, since the power is distributed over a smaller area, the power density, I can say, what you can call is the power density is basically the power per area. Okay. So when you are closer to the source, the amount of power available will be more and your area is same. So the power density is larger when you are near to the source. And the power density will be very, very less when you are moving far away from the source. That is the reason why there is an introduction of the waveguides. Now what will happen? See, the wave is trying to expand out in all the directions like X, Y and Z directions. Suppose I want to restrict the expansion of the wave in X direction. So let us assume that there are two conducting plates located at X is equal to 0 and X is equal to A. What will happen in this case? Even though the wave is trying to expand out, these waveguides are made up of a perfect conducting material. So as a result, what will happen? Even though it is trying to expand out, it will again get reflected back. Again, it will get reflected. So it is going to move on like this. So what actually you are doing in this case? By putting the waveguide, you are making sure that the wave cannot expand beyond this waveguide. Then what will happen in that case? Even if you take a same area here, same area very far, since there is no loss of power, because the power density is completely going to be uniform. Are you getting my point? The moment once you put a waveguide here, you are going to restrict the expansion of the wave in the x direction. So if you choose any surface also in the same direction, since there is no losses, power will be uniformly distributed between these two plates. Even if you consider the area here, even if you consider the area here, your power density remains same. So the main purpose of the waveguide is to make a uniform power density throughout the distance. Is it clear what I'm saying? Any questions you can ask now? Okay. So in today's lecture, actually what we are going to see is the complete theory part of the waveguides. And in the next class, we are going to discuss the problems. Because I thought solving the problems is not a complex thing when you consider the waveguides. Just you completely understand the complete theory part. Then it is easy when you are discussing about the problems. So the main thing when I summarize here the waveguides are used at gigahertz frequencies. And the waveguides are used basically to maintain a uniform power density throughout the distance. So you can see here there are different type of the waveguides are there. Parallel plate waveguides, just now I have seen. But you can see here as the wave trying to propagate, it is going to expand out in all the directions. If we keep the set of plates only in the x direction, this configuration is said to be parallel plate. So suppose if you are keeping the plates something like this in x direction as well as the y direction, the wave is going to restrict in 2 dimensions. That we are calling it as a rectangular waveguide. And what will happen? Suppose if you want to store the energy, if you want to store the wave in a particular configuration, you can assume that that is basically said to be closing in all the directions. That is basically said to be the cavity resonator. So the cavity resonator is a configuration where you are bounding the wave in a particular configuration by keeping the plates in all the directions. Okay, so that is what the actual difference between the different waveguide structure. And actually, you've seen in the latest syllabus, there has been added a circular waveguides also. That we are going to discuss a little bit afterwards. Okay, we will postpone that discussion because there is a similar when you want to discuss about parallel plate and rectangular waveguide. First, we will complete that part. Then we will focus our attention to the circular waveguides. Rectangular waveguide has only 2 dimensions. 2 dimensions, yes, correct. Because in a rectangular waveguide, what you are going to do, you are going to keep a set of plates in x is equal to 0 and x equal to a, and even at y is equal to 0 and y is equal to b. As you can see here, the top plate you can consider it as x equal to a, the bottom plate is x equal to 0. And the side wall, you can see here, this is y is equal to 0. This one, you can consider it as y equal to b. And assume that the wave is propagating along the axis of the rectangular wave. There are 2 set of plates will be there. So when it consider that, you can see that the length and the width. Yeah. So first we will discuss about parallel plates. The concept what we are going to discuss in parallel plate waveguide, everything remains same even if you go for the rectangular waveguide. Just there is only one additional thing that the wave is going to restrict in another dimension. Okay. So in case of a parallel plate waveguide, I started with considering there are 2 plates located at x is equal to 0 and another plate located at x equal to a. And remember, by seeing it looks like line, it's not a line, it is basically a plane. So assume that there are 2 conducting plates located at x is equal to 0 and x equal to a. So what will happen when I try to launch a wave? It is going to enter at a certain angle. So the wave is trying to enter at a certain angle based on the operating frequency. That we will see what is the wave angle later. So once the wave is trying to hit here, what will happen since this is a conducting plane, whatever the angle at which it is going to incident here, it is going to reflect back. Because the conductor cannot allow any electric field to go out of it. So whatever the signal is going to enter here, the fully thing it is going to reflect back. Again, this is also a conducting surface. It is going to re-reflect again. So that is how the uniformity is going to maintain in case of a parallel plate waveguide. But actually, what is the thing to understand here? This is kind of propagation. Don't have a waveguide. When you don't have a waveguide, actually the wave is happily propagating in the z direction. There is no concept of total internal reflection. Because when you see in free space, there is no conducting plates, so there are no reflections. So the wave is actually propagating in the z direction. But the moment once you introduce the waveguides, the direction of the propagation is going to be changes. So this is your actual direction of propagation. So can you tell me what are the components that direction of propagation consists of? How many components the direction of propagation is going to have? Have a look on this. Yeah, tell me. Good. X and Z. See, if you consider this is the direction of propagation, you can say one component is along the axis, that is Z, and there is another component between the walls that is along X direction. So the only difference is that. So in case of a parallel plate waveguide, so you can see here the direction of propagation consists of X and Z. Or you can say the plane of incidence is basically said to be in the XZ plane. I hope you already know what is the plane of incidence means. We have discussed in the oblique incidence. So the plane of incidence means in which plane the direction of propagation is completely lying. So in this case, the direction of propagation lies in the XZ plane. So I can call the plane of incidence is a XZ plane. So subjected to that, next we are going to discuss about some mathematical theory part. So first we started with the wave equations. So we are having the wave equation says del square E is equals to gamma square E. And what is gamma represents? Gamma is the propagation constant in this medium. So suppose if we have a phase present between the two conducting plates, so what is the gamma represents? Is the propagation constant in the resultant XZ plane. Suppose what I will consider, I will assume that there is a free space present between the two conducting plates. We know that the equation for propagation constant is gamma square is equal to j omega mu into sigma plus j omega epsilon. Okay. In free space, what is the conditions? Sigma equal to 0, mu is equal to mu naught, and epsilon equal to epsilon naught. So subjected to that, what is the value of gamma square you are going to get? J omega mu naught into j omega epsilon naught. Okay, so gamma square value I can it as minus omega square mu naught epsilon naught. So you just take it as this as equation and this as equation 2. So any questions till now? So first I was going to solve the wave equations. So for that I was defining what is my propagation constant. So I started with the wave equation and I have defined what is the actual propagation constant by assuming that there is a free space present between two conducting plates. Any questions you have? So next what we will do, we'll try to solve the wave equation. Similarly, what we have done in the wave propagation. So we'll try to solve like this. So del square E is equal to gamma square E, where gamma square is equal to minus omega square mu naught into epsilon naught. Right. So since the actual direction of propagation consists of x and z, so when I try to expand this del square E, we should write it as dou square E by dou x square plus dou square E by dou z square is equal to gamma square E. So can you tell me how to write this equation in waveguides? In parallel plate waveguide, you are not going to restrict the wave in direction. Okay, the wave is going to restrict in the x direction and it is going to advance in the z direction. So since you are having the variation with respect to x and variation with respect to z, and since you are not doing anything in the y direction, so the rate of change will be 0. So that is the reason why I have not considered y dimension. Whereas in case of a rectangular waveguide, you have to additionally add dou square E by dou y square here. So that is the only change. And we know that when the wave is trying to propagate along the z-axis of the medium, the wave is trying to exponentially decay with the increase in the distance, right? So let me generalize it. So when you are generalizing the equation in electric field in z direction, you already know for any type of wave, it has to exponentially decay with respect to distance. So let me call it as E naught into e power minus gamma bar z. So there is a difference between gamma bar and gamma you have to understand. Okay. You can see here, this is your resultant propagation, right? So the propagation constant, I can call it as gamma. And the propagation constant in z direction, I can call it as gamma bar. And similarly, along this, I can represent it as a gamma x. So gamma is the resultant propagation constant. Gamma bar is along the z direction. Gamma x is along the x direction. Okay. Now, when you assume the electric field intensity is something like this, you just calculate what is the value of dou square E by dou z square. Okay. So first you start with dou E by z. You are going to get minus gamma bar E naught e power minus gamma bar z. Okay. Dou square E by dou z square is equal to, you are going to get gamma bar square into E naught e power minus gamma bar z. So that is same as gamma bar square into E. So please cross check if there is anything wrong, you just correct. Is it correct? So substitute this value of dou square E by dou z square in this equation. So from this equation, what I can try to say, dou square E by dou x square gamma bar square into E is equal to, and I already know the value of gamma square is something like this, minus omega square mu naught epsilon naught into E. So in other words, so let it bring to the left side. So what you are going to get, dou square E by dou x square plus gamma bar square plus omega square mu naught epsilon naught into E is equal to 0. So let me put as some constant gamma x square. So how I will write the equation here, dou square E by dou x square plus gamma x square into E is equal to 0, where your gamma x square can be written as gamma bar square plus omega square mu naught epsilon naught. So this is very, very important equation you have to remember. So ultimately my intention is just to solve the wave equation and find out what is an equation for electric field you are going to get. Okay. So any questions till now? Right now? Shall I go ahead? So what equation you are getting? Dou square E by dou square plus gamma x square into E is equal to 0. And you are assuming gamma x square is equal to gamma bar square plus omega square mu naught epsilon naught. Again the same thing, when I go to the rectangular waveguide, all these equations and all I was not going to do. Straight away I will start with this equation. Additionally, gamma x square, you are going to have gamma y square. Okay, straight away I will start with this equation in rectangular waveguides. The process. Okay, now you are having this differential equation, and what you do, you try to solve this differential equation and give me an equation for electric field. So please do that. You take some time and tell me what is the solution for electric field intensity you are going to get. So once you are done with that, you just let me know. Okay, tell me what all the values you are getting. Yeah. So first, what are the roots for this you are getting? The roots will be plus or minus j gamma x. Agree? So when you have the root something like this, alpha plus or minus j beta, equation will be of the form something like this: e power alpha x c1 cos beta x plus c2 sin beta x. Okay. By comparing this, your alpha will be 0 here. If you compare this one with this, your alpha will be 0 and your beta will be same as gamma x. Okay, so with that, I can say the electric field variation in x direction can be given by C1 cos gamma x into x plus C2 sin gamma x into x. So this is the equation for electric field with respect to x direction. So we know what is the variation with respect to z already. Okay. So if you combinedly write both x and z variation, how will you write? So whatever the variation you got right now, C1 cos gamma x into x plus C2 sin gamma x into x into e power minus gamma z. So this gives the combined variation of electric field with respect to x as well as z. Okay, forget about the z variation, we already discussed that. So this is the electric field variation in x direction. Now there are certain conditions here. When you are writing this electric field intensity at x is equal to 0 and x is equal to a, since both these are perfect conductors, the electric field intensity will be 0. So we see inside a perfect conductor, the electric field intensity will be equal to 0. So first, when you start with x is equal to 0, your electric field is 0. So how to write this equation then? So 0 equal to C1 into, so cos 0 will be 1 plus C2 into sin 0 will be 0. So you are going to get the constant C1 is straight away equal to 0. And similarly, at x is equal to a, your electric field is 0. So which means that electric field is 0 is equal to, anyhow C1 is already 0. So using this equation, your C1 will be already 0. You need not to worry about that. So what you are going to get next thing, C2 into sine gamma x into x. So what is this equation says? Sorry, it's not x, it is a. After substituting x is equal to a, it is gamma x into a. So this equation, you're getting sine gamma x into a is equal to 0. So can you tell me accordingly, what is the value of gamma x into a? Very good. It is m pi. So where m can ideally starts from 0, 1, 2, etc. and that. But I will tell you, m is basically stands for mode number here. In case of a parallel plate waveguide, m is equal to 0 doesn't have any meaning. So I will give an explanation later, you can understand. So here you can assume that m starts from 1. So when I go to the mode of operation, you can clearly understand why m is equal to 0 is doesn't exist. Okay. Now what is the value you are going to get? Gamma x is equal to m pi by a. So this is your very, very important equation. By solving the wave equation, you have arrived the solution for electric field intensity, and you are going to discuss about the propagation constant. And once you know the value of gamma x, you can easily define what is gamma bar using this equation. And what is the change when you are going to do in rectangular waveguides was, in addition to the x plates, see, x is equal to a and x is equal to. So similarly, you will have another set of plates is equal to 0 and y is equal to b. Can you tell me what is the propagation constant in y direction you are going to get using the same equation? The same equation you are going to get, and in terms of y. Again the same story. At y is equal to 0, your electric field is 0. Y is equal to b, your electric field is equal to 0. So in rectangular waveguides, what will happen? Similarly to the same equation, instead of a, you are going to get b. So let me write that integer as n into pi by b. Because the same thing, whatever you done for the x direction, the same thing you have to do for the y direction. Is it clear? Whatever I said? So you can ask any questions. You are free to ask because the concepts were very important here. You just understand the concept. Forget about the problems as of now. Right. You can reply. Am I audible to you? I was keep on repeating, but there is no response from you. Okay. First, we'll discuss about the propagation constant then. Okay. So since the wave is propagating in this, the resultant propagation constant is gamma. So after you resolving, along z you are defining as bar, along x you are going to define it as gamma x. Okay. So what is the relation between these three you already got? I can use this equation and I will try to find what is gamma bar. So gamma x square is equal to gamma bar square plus omega square mu naught epsilon. So which means your gamma bar is equal to root over gamma x square minus omega square mu naught epsilon naught. So what is the propagation constant gamma bar you are getting right now? So we know the value gamma x is equal to root over m pi by a whole square minus omega square mu naught epsilon naught. So let me consider the first case where m pi whole square is greater than omega square mu naught epsilon naught. What will happen in that case? What happens to your gamma bar? Is it purely real or imaginary or complex? Yeah, gamma bar is purely real. Ideally speaking, you know that the propagation constant is in the form of alpha plus j beta. And when you are getting this case, suppose if the frequency is satisfying this condition means you are getting gamma bar is purely real. Is it your desired case? Purely real means it is the attenuation part. So you don't want this to be happening in case of a waveguide, isn't it? When I say bar is real, the wave is going to be completely attenuated because the real part indicates only the attenuation part. Okay. So you can say that full attenuation will exist. So what is your desired case right now? It's ulta. So this term has to be higher than this one. So then your gamma bar is purely imaginary and your real part will be 0, which means your attenuation will be 0. So what is the condition right now? When omega square mu naught epsilon naught is greater than m pi by a whole square, your gamma bar is purely imaginary and you don't have any attenuation. Is it clear? So from this, what you are understanding, all the frequencies cannot be transmitted in a waveguide. Only the frequencies which are satisfying this particular condition is going to propagate without having any attenuation. So we are going to define that starting frequency as the cutoff frequency. Okay. So when you find the cutoff frequency, you just equate these two terms. That gives the starting frequency beyond which you can expect there will not be any attenuation. So in the next section, what we are going to discuss, by equating these two, we are going to find out what is the cutoff frequency for that. So as of now, the conclusion here is when the frequency is below the cutoff frequency, the wave cannot propagate. When the frequency is more than cutoff frequency, the wave can happily propagate without any attenuation. Okay. To find the cutoff frequency, what I need to do, I have to equate the omega value, omega square mu naught epsilon naught is equal to m pi by a whole square. So let me define omega is to omega c. Okay. So using this, what you are going to get, omega square is equal to 1 over mu naught epsilon naught m pi by a whole square. So you know that 1 by mu naught epsilon naught is said to be c square because velocity of light we have defined it as 1 over root mu naught epsilon naught. So when I say c square is equal to 1 by mu naught epsilon naught. So you can remember this. So c square into m pi by a whole square. So based upon this equation, I can say omega c is equal to c into m pi by a, and omega is equal to 2 pi fc is equal to c into m pi by a, and you are going to get the equation for frequency as mc by 2a. So this is very important equation in parallel plate waveguides. So what is basically FC says here, when the frequency is lesser than cutoff frequency, there will be fully attenuation. And if your incoming frequency is more than the cutoff frequency of the waveguide, the wave can happily propagate without having any problem with the attenuation. Okay. So when you see the propagation characteristics, let us say this is your propagation aspect and this is your frequency one. So when the frequency is below the cutoff frequency, there is no propagation. And when the frequency is above the cutoff frequency, you can estimate that there is no attenuation. Can you tell me what kind of characteristics it is? What is the response you are seeing from here? Good. So that is the reason why you can say that the waveguide will act like a high pass filter. Because below the cutoff frequency, it is not allowing the signal, and above the cutoff frequency, it is going to allow. And I told you in the starting point, you cannot design the waveguide, especially at the low frequencies. You can see the reason right now. Suppose if I want to get my waveguide cutoff frequency in kilohertz, you can see here what should be the dimension. If the frequency, cutoff frequency goes low, your dimension of the waveguide is going to be bigger. So what is this A represents? A is the spacing between the plates. So if you want to design the waveguide at low frequency, this will come in the order of some kilometers. Okay, that is the practical reason why you cannot design the waveguide at low frequency. So suppose if the same frequency falls in gigahertz, your dimension will come in the order of centimeter. So any questions regarding the cutoff frequency? Okay, I will go ahead then. So the next thing is the phase velocity. The phase velocity definition is we are following the same thing. So tell me what is the phase velocity for? It is basically the ratio of omega and beta. Since from the propagation we are using the same equation. So once again, if you have a look on the propagation constant, what it is going to be happen, that is equal to root over m pi by a whole square minus omega square mu naught epsilon naught. So what is your intended case? In order to have the propagation, your omega square mu naught epsilon naught must be greater than m pi by a whole square. So in that case, what will happen? Gamma bar can be written as purely imaginary, right? So that is equal to j into root over omega square mu naught epsilon naught minus m pi by a whole square. Will you agree with me if I write like this? Agree or not? So when you are writing in terms of the complex number, you can interchange that. Yeah, it is just only the simple formula. Root of 1 minus 4 can also be written as j into root over 4 minus 1. The same concept I have followed. So by comparing, it is purely of the form j into beta, and your real part is 0. So the propagation constant here you are getting is equal to root over, take omega square mu naught epsilon naught common, you are going to get 1 minus m pi by a whole square into 1 over omega square mu naught epsilon naught. So what will happen? When it comes out from this root, it is going to get omega by c. Agree? Over 1 minus m pi by a whole square into 1 by mu naught epsilon naught can be written as c square divided by omega square. So from this, what is the phase velocity? The phase velocity is equal to omega by beta. So what you are going to get? C divided by root over 1 minus m pi c divided by a omega whole square. So the phase velocity can be written as c divided by root over 1 minus m pi c by a into 2 pi f whole square. And we know this mc by 2a is basically called the cutoff frequency. So I can define the phase velocity is equal to c by root over 1 minus fc by f whole square. So any questions here?
So, why
Yeah.
why is it that we're converting it to imaginary? Instead, can't we take the alpha? Like, can't we take the real part to be alpha?
No, here real part is not happening, right? Because the second term is higher than the first term. It is something of this
Okay,
form only.
okay.
Yeah. So when the second term is higher, you are going to get it. The result is a imaginary part, purely imaginary. Yeah.
Okay, so
Yeah. So finally, you are going to get the phase velocity is something like this. You just go through the derivation part. So finally, how to remember this equation?
So it will be like 1
Hmm.
minus 2 fc by f, right?
2fc, yeah?
Yeah, because fc is mc by 2a.
Yeah. mc by 2a itself is fc. I have replaced that. Divided by f is there.
Oh, okay, okay, that is 2 pi f. Yes, yes.
Yeah. Okay. So you are going to get the phase velocity is equal to c by root over 1 minus c by f whole square. So here you have to notice one point. If you want to expect any propagation in the waveguide, your operating frequency should be higher than cutoff frequency. In that case, what will happen? If your frequency is greater than the cutoff frequency, in the denominator, you are going to get less than 1.
So there is a delay, means like if you're writing
Yeah,
it
yeah.
not
Yes, I was seeing that also.
okay.
Yeah. Now is it okay? So when the frequency is greater than the cutoff frequency, your phase velocity, what it is going to become? So if f is greater than fc, in the denominator, you are going to get lesser than 1. So in the denominator, if you are lesser than 1, what happens? Your phase velocity will be more than the velocity of light. Is it clear? Do you have any questions here to ask? Yeah. But the thing is, in reality, you cannot imagine that any signal propagates with a velocity more than velocity of light, right? So basically, till now, it is very hard to understand that you cannot imagine any signal with a velocity more than velocity of light. But actually, the mathematics is saying that I can justify the same statement with a practical thing. Okay. So for that, you can see here, this is your two conducting plates, right? If you don't have any waveguide, you don't have these two plates. Happily, the wave is propagating in the free space like this. Okay. In that case, what is your velocity? If you don't have any waveguide and this is your free space, so your wave is not having any reflections. So the wave is happily propagating like this. Can you tell me what is the velocity associated with that? Good. It is nothing but your velocity of light. Right? Velocity can be written as wavelength times frequency. So what is the actual wavelength you have covered right now? When you don't have waveguide, what is the wavelength you have to consider here? That is from here to here. So wavelength is basically defines what is the distance traveled by the wave in order to have a phase difference of 360 degrees. So you can see in the diagram, this is the point to this point, the wave has traveled to repeat the same point again. Or you can say for the 360 degrees phase shift. So the corresponding wavelength, I can call it as a lambda naught, which represents the free space wavelength into F. So lambda naught basically called as free space wavelength. Which means if you don't have any waveguide, the wave can happily propagate in the axis. So that axial distance, I was calling it as lambda naught. Is it clear? Yeah. Now what will happen the moment once you introduce the two conducting plates? I can call that velocity as the phase velocity. So the phase velocity is coming into the picture when you introduce the waveguide. So when you introduce the waveguide, what will happen? To cover the distance from here to here, the wave is actually traveling more distance, isn't it? To cover the same distance, whatever is there in free space, now the wave is taking a longer path to cover the same distance because of the reflection. Will you agree with my point? Yeah. Whatever this longer path I have defined, I can call it as a guided wavelength because that is a wavelength when you are introduced the waveguide. So I can define the phase velocity as a lambda g into f. So where lambda g is nothing but the guided wavelength. So what will happen? Since by observation, guided wavelength is your guided wavelength is higher than the space wavelength. What you can say? Your phase velocity is more than velocity of light. You can see these two equations. And since your guided wavelength is much larger than free space wavelength, you can estimate the phase velocity can be more than velocity of light. Agree? Do you have anything to clarify? So the moment once you put the waveguide, the wave is taking a longer path to cover the same distance, whatever you have done in the lambda g part. Lambda g part, I was telling you, right? The moment once you introduce the waveguide, to cover the same distance, it has taken a longer path. So this longer path, the total distance, I was calling it as a guided wavelength. Okay, because even in the same lambda g, the signal is undergone a phase shift of 2 pi radians. But when you introduce the waveguide, it is taking a longer path. When you don't have any waveguide, it is taking a shorter path. So since your guided wavelength is more than the lambda naught, your phase velocity is more than velocity of light. So what is the final thing I can say? The phase velocity is equal to lambda g into f is equal to c divided by root over 1 minus fc by f whole square. So there are two things here and three things in terms of the wavelength is concerned. So basically lambda naught is called free space wavelength. That means when you don't have any waveguide, the distance traveled by the wave in the free space to undergone a 2 pi radians is said to be lambda naught. And lambda g, what is that called? It is called the guided wavelength. That is the distance traveled by the wave inside the waveguide to undergone a phase shift of 2 pi radians. And there is one more wavelength which I can call it as a cutoff wavelength. Cutoff wavelength is a recipient of the cutoff frequency, right? We know what is a cutoff frequency formula, right? MC by 2F. So similarly, in terms of the wavelength, if you want to define, so the cutoff frequency represents the minimum frequency that is allowed in a waveguide. So in terms of cutoff wavelength, if I want to define, that is equal to C by FC is same as 2A by M. So when the frequency is minimum, your cutoff wavelength is maximum. So lambda C, I can call it as a cutoff wavelength or the maximum wavelength that is allowed inside the waveguide. So using this equation, okay, you know that Fc by F can be written as reciprocal of the wavelength, and if you simplify, you are going to get this equation. Okay, you know that C by F is basically said to be lambda naught, and Fc by F you can replace it as lambda naught by lambda C. So after doing some rearrangements, you are going to get this particular equation. So you can take it as an assignment. So you know all the differences between these three wavelengths and take this equation and prove that this value is going to be satisfied. And once you are done with that, you can enter your answers in the WhatsApp group. Okay. Any questions here right now? I'll go ahead. Next thing comes is the group velocity. Basically what you have defined, the phase velocity is equal to omega by beta. So the phase velocity comes into the picture when the phase variation with respect to time and phase variation with respect to distance both are linear to each other. Which means this comes in the picture when your beta is proportional to omega. But when is the concept of group velocity comes was if the phase changes with respect to distance is not in linear with phase changes with respect to time. So suppose if your beta and omega are non-linear, you can define it as a group velocity rather than saying it as a phase velocity. I will give a simple example. Suppose if you have a single wave propagate in a waveguide, you can say that omega and beta are linear. But what will happen if you try to launch a number of waves? Each particular wave corresponding to a frequency and a corresponding phase shift. Okay, so when you are simultaneously launching a beam, you can say beam of waves, your beta and omega will be non-linear. So in that case, you can call the average velocity using this equation, that is a d omega by d beta. Anyhow, this is same thing your mathematics what I have studied. When anything is non-linear, you can say dy by dx. When it comes to the linear, you can say it is y by x. So the group velocity comes in the picture when beta and omega are nonlinear. So what is the value of group velocity if you want to calculate? So let me go back to the value of, yeah. I think I have raised that. Okay, anyhow, when you see the propagation constant gamma bar, you are getting it as root over j into root over omega square mu naught epsilon naught minus m pi by a whole square. So it is of beta. Okay, by comparing, you can say beta is equal to root over omega square mu naught epsilon naught minus m pi by a whole square. So this is the same thing when we have done the phase velocity, right? Just 1 second I was writing that. So what you can do, you differentiate the value of beta with respect to omega and then take the reciprocal of that. First take the differentiation of beta with respect to omega and take the reciprocal, you are going to get the group velocity. So what is the group velocity you are going to get is nothing but c into root over 1 minus fc by f whole square. So please cross check if you have the time, but the approach is this. Take the differentiation of beta with respect to omega and take the reciprocal. So what is the summary here? The phase velocity comes into the picture, your omega and beta are linear to each other. So that value is equal to c by root over 1 minus fc by f whole square. If omega and beta are non-linear, your group velocity will be defined as d omega by d beta. That you are going to get c into root over 1 minus fc by f whole square. So using this, you can verify that the phase velocity into group velocity is equal to c square. This is a very, very important relation. So please ask me if you have any questions before going to the next concept. So if you have any questions, you can ask. If you don't have, at least say. So the next thing is a wave angle. Wave angle is basically nothing but the angle at which the wave is trying to enter inside a waveguide. Okay, so you can see here, this is your waveguide, right? Two conductors are. So the wave is trying to enter at a certain angle. So basically that depends on the particular frequency. Okay, so what is the assumption here was when the frequency is exactly equal to cutoff frequency, the wave is trying to enter at a wave angle of 90 degrees. So by taking this as a reference, they have formulated the wave angle sine theta is equal to fc by f. Okay, so what is that meaning says? Suppose if your frequency is same as the cutoff frequency, you can see here that the theta will be 90 degrees. So how that theta value will be measured here? The angle made by the wave with respect to the axis of the waveguide. So when the frequency is same as cutoff frequency, you can see that with respect to the axis, there is a 90 degrees angle. Okay, suppose if the frequency is 2fc, 2 times the cutoff frequency, what is the wave angle you are going to get? Tell me. So when the frequency is 2 times of fc, you are going to get sine theta is equal to 1 by 2. Okay, theta is equal to 30 degrees. So what is the reference here? They have considered the cutoff cutoff frequency is assumed to have a wave angle of 90 degrees. And based upon the cutoff frequency, the wave angle can be defined using this formula. Sin theta is equal to Fc by F. And one more point here you have to remember. What is that point? The wave angle depends on the mode of operation. Okay, what is that mode and first mode, second mode, all these things and all we are going to cover now soon. Okay, so the wave angle is defined as the angle made by the wave with respect to the axis of the waveguide. And the wave angle is considered to be 90 degrees if frequency becomes the cutoff frequency. Okay, having said that, when we go to the modes of operation, this is very important concept. Basically, the mode is defined with a two subscripts. Okay, let us say either it can be transverse electric or it can be transverse magnetic or transverse electromagnetic. The mode is basically represents with two subscripts. So what is this two subscripts indicates? M and N represents the number of half cycle variations of electric field along X direction and along Y direction. So let us talk about parallel plate waveguide. So this is your parallel plate waveguide. Okay. X is equal to 0 and X is equal to A. So what I mean to say, between these two conducting plates, if you see the electric field, if it is having one complete half cycle, I can call this mode of operation is the first mode. And one more thing, are you doing anything in Y direction here? In parallel plate waveguides, is there anything in the Y direction? Yeah, which means that your N value can be equated to 0. So in parallel plate waveguide, I can assume that if you keep the plates in X direction, you are not doing anything in the Y direction. So there are no variations in Y direction. Will you agree with me if I say N is equal to 0? Agree? Since there is nothing you are going to do in the Y direction, you cannot restrict the wave in the Y direction. So the second subscript can be equated to 0 in case of parallel plate. But this is not the case when you are going for the rectangular waveguide. Okay, in rectangular waveguide, you are keeping the set of plates in X direction as well as the Y direction. Okay. Now you would have been understand till now in our discussion when I was discussing Fc is equal to mc by 2a. Already the second subscript is equal to 0. So suppose if m is going to start from 0, t is 0, 0. Does it have any meaning? So when I say m is equal to also 0, there is no electric field in y direction, and in turn there is no electric field in x direction as well. Which means that your electric field itself is not existing. Because if the wave is propagating in the z direction, your electric field should be there either in x or y. So since you are not doing anything in y, your n will be 0. And suppose if we start with m is equal to 0, which replicates, there is no electric field in x direction as well. So which I can assume it as there is no electric field. So there is no electric field means there is no wave at all. So that is the reason why I have considered the minimum value of m is started with equal to 1. Do you understood the concept? Why the minimum value of m has to be start from 1? Is it clear? Is it clear? Why the m value should not be 0? So the next thing, suppose if you understand this, so try to answer this one. So I had two conducting plates here. I had one half cycle, okay, and there is a part of the second half cycle is. Can you tell me in which mode it belongs to? First mode or second mode or whatever the mode it is. You tell me which mode it belongs to. This is my electric field. One complete half cycle is there and a small part of the second half cycle is also there. So can you tell me in which mode it basically belongs to? Reply quickly. We don't have the time. It is 2. It's basically, remember, I forgot to mention here, this is represents the complete half cycle. How many complete half cycles are there between the plates? So in this example, there is only one complete half cycle is there. So it also belongs to first mode only. So why I was telling you this one was, there is a misconception that, so when I say the first mode, you may expect it that only one frequency will be present. So in the first mode, there will be a bunch of frequencies will be existing together, starting from one complete half cycle until it approaches the second half cycle. So all the group of frequencies which have one complete half cycle to approaching two complete half cycle is false in the first mode. Similarly, complete two half cycles approaching to three half cycles, you can call it as a second mode. So agree what I'm saying? Are you understanding? So when I classify all the group of frequencies, you are having a number of frequencies like this. So when I say this is your cutoff frequency, right? MC by 2. So when I say the first mode, yeah, please ask any question.
Sir, I thought like frequency will be half, then wavelength will be double. That's why mode 2. It's not like that.
Which one?
Sir, if frequency is half, then wavelength will be double. So it's not like that, right?
No, no, no. That is just only the theoretical representation I have given, but that is not in terms of the wavelength. But just assume to interpret that, you will have a group of frequencies. I have told like that, but it's
Okay.
not wavelength and frequency related thing and that.
Okay.
Just to give a simple example, but that is not true. To give a simple example that there will be a group of frequencies in each mode, I have represented with that. So there is no relation between wavelength and frequency here. Okay.
Okay.
So the thing, whatever the group of frequency I was calling it as, no, you can see here. Here I was saying it here. So suppose when I say the first mode, the cutoff frequency is C by 2A. Okay, because your M is equal to 1. So how the group of frequencies is classified was, so when the frequencies is ranging from FC1 to 2FC1, you can call all these frequencies as a first mode. Agree? So similarly, when the group of frequencies is lying from 2FC1 to 3FC1, you can call it as a second mode. And third mode, it is 3FC1 to 4FC1. It is called your third mode. Okay, whatever I have discussed in the wavelength concept, that is just to give an idea that there is a group of frequencies, I have told that. But actual definition is different. So as per the frequencies wise, if you consider the first mode of frequencies ranging from FC1 to 2FC1. And second mode ranges from 2FC1 to 3FC1 and so on. Clear?
Yes.
Yeah. Now, can you tell me what is the wave angle right now corresponding to that? So as I said, in the first mode, you will have a group of frequencies, right? Similarly, you will have a group of frequencies in the second mode and third mode. So what is the basic definition for wave angle? So here you have to concentrate here. The wave angle definition is sine theta is equal to Fc by F. But when you are talking about a particular mode, and if you define the wave angle in that mode, you have to consider that particular cutoff frequency. What is the cutoff frequency for third mode?
3
Reply
F.
here. 3fc1. Yes. Cutoff frequency means starting frequency. So when you see in the first mode, what is the wave angle for f is equal to fc1? When the frequency is same as the cutoff frequency, what is the wave angle you are going to get? So your cutoff frequency is fc1 and frequency is also fc1. So what is the wave angle you are going to get? 90 degrees. Okay, so when you see in the waveguide, you will have a wave angle from ranging from 90 degrees up to. So what will happen when the frequency is approaching to fc1? The wave angle can be defined as fc1 by 2 fc1. So sine theta is going to become 1 by 2. So theta is going to become 30 degrees. Agree? So when you see in the first mode, the group of frequencies from fc1 to 2 fc1, and the wave angle is going to range from 90 degrees to 30 degrees. Okay. Similarly, can you tell me in the second case? Can you do it in the second case and tell me? Yeah. So what will happen in the second mode? In the second mode, if you want to define the wave angle, you have to define sine theta is equal to 2 fc1 by f, because cutoff frequency is 2 fc1. And when the frequency is 2 fc1, what is the wave angle? Tell me quickly. Reply. When the frequency is 2 fc1, when the frequency is also 2 fc1, what is the wave angle?
So the cutoff frequencies will also be like 2 FC1 for the second
Yeah,
case.
that's what I told you, right? What is the definite? I told here.
Okay.
Wave angle depends on the mode of operation. So when you are defining the wave angle for the second mode,
Make it 90 then. Okay. So always
yeah,
it's 90 and 30.
yeah. Again, it is 90 and 30, yeah?
Inverse of 30.
No,
Uh,
yeah,
2 FC 2 by 3.
yeah, yeah. 90 degrees to sine inverse 2 by 3.
Yes, sir.
Okay, sine inverse 2 by 3 means you can say approximately 41 degrees. You can calculate, it will come to 41 degrees. So the wave angle is ranging from 90 degrees to 41 degrees. So similarly, tell me for the third one, third mode. Quickly tell me for the third one, what is the wave angle ranges from?
So again 92 sine inverse 3 by 4.
Yeah, good. 90 degrees to sine inverse 3 by 4. So sine inverse 3 by 4 is approximately 48.5 degrees. Okay, so what is an observation you can get here? In the first mode, the range of the wave angle will be high, which means you are having from 90 degrees to 30 degrees. So the wave can enter at any angle, which can range from 90 degrees to 30 degrees. Okay, whereas when you see the second mode of operation, it can extend from 90 to 41 degrees. So the range is a little bit compressed. Okay, the wave angle can enter only from 90 to 41. Okay, when you go to the third mode, the wave angle is much compressed. So you can have the wave angle ranges from 90 degrees to 48 degrees approximately. So what is the observation here? As the mode number increases, the wave angle range is getting decreased, which means that the wave can enter over a small range when you go to the higher order modes. So in the first mode, you will have a plenty of range. The wave can enter at 90 degrees, 65 degrees, 40 degrees, also on and so on. Whereas in the second mode, the wave can enter over a certain range of wave angle. Okay, and whereas if you go to the higher order modes, the wave angle range is very, very less. You got my point, what I mean to say? At high frequencies, when you go, if you go to 10th order mode or 11th order mode, the wave angle hardly you can expect it from 90 degrees to let us say some 60 or 70 degrees. It cannot reach 30 degrees as we have discussed in the first mode. Is it clear, that point?
Yes.
Yeah. And one more thing you can notice here, the same wave angle is getting repeated in different modes. Is it possible or not? You can see the same wave angle is possible for all the modes. Is it happening or not?
Okay, the ratio will be like that.
Exactly. You can see here 90 degrees. 90 degrees is there in all the modes.
Yes.
Whether it is first mode or second mode, all the things are there. So you can see that the wave angle can be repeated between two different modes. But what is the important thing? The same 90 degrees cannot be possible for two different frequencies in the same mode. Which means in the same mode, if you consider two different frequencies, you will not get any 290 degrees angle.
Yes, sir. Yes.
Yeah. So the same wave angle is possible for two different frequencies belongs to two different modes. If you take one frequency from here and if you take another frequency from here, you will have the same wave angle. But it cannot be the case if you take two frequencies from the same mode and you cannot expect the same 90 degrees angle. Clear? So
Sir,
that is a group of, yeah, tell me.
can that definition like that related to half cycle means like mode one
Yeah.
means
Yeah, half cycle. I'll come back to that once again. See, when it comes to the half cycle, what is the condition I told you? So this is x equal to 0 and x is equal to a. So let me define the cutoff frequency by assuming in terms of our definition. So what is the condition I told you? When you have a complete half cycle, I can call this is my first mode, which means cutoff wavelength. So when you have only one complete half cycle present between two conducting plates, this you can consider it as the first mode. So in the first mode, what is the separation between these two you are having?
separation is always constant, A, right?
Yeah, in terms of the wavelength, I was talking about wavelength. Your question is in terms of wavelength, right? Yeah. When you have a complete cycle, and if you take only half of that, so what is the total distance here between here?
Lambda by 2.
Yeah, yes. So when you see the first mode cutoff wavelength, if you want to calculate cutoff wavelength, I was talking specially. So condition lambda by 2 should be equal to A. Agree. So what is the condition? Your cutoff wavelength has to be 2A. So what is this cutoff wavelength basically represents? That maximum wavelength allowed. Agree?
Yes,
Because it is a ratio of cutoff frequency. So when the frequency is minimum, wavelength is max. So similarly, can you tell me for the second mode, what is the cutoff wavelength? Second mode means you can expect complete two half cycles.
okay.
So can you tell me what is the distance from here to here right now?
Lambda.
Yeah, lambda. I can define it as this is a cutoff wavelength for the second mode is equal to
A, sir.
yeah. So which means you can write it as 2A by 2. Yeah. When
Okay.
you see for the third mode,
Third mode means
there
3
are
lambda.
three half cycles will be there, which means 3 times lambda by 2. Agree?
Yes, sir.
So let me define it as a cutoff wavelength for the third mode is equal to A. So what is the cutoff wavelength you are getting? 2A by 3.
Yes, sir.
Yeah. Similarly, when you are generalizing, what is the cutoff wavelength for the mth mode? So when you have first mode, you are having 2A by 1. Second mode, 2A by 2. Third mode, 2A by 3. and so on. So what is the cutoff wavelength for mth mode?
2a by m.
Yeah, 2a by m. So this is basically equal to C by Fc, cutoff frequency.
Yes.
Wavelength is a C divided by Fc. So what is the condition you are going to get? Fc is equal to okay, mc by 2a. See, the same equation we have got with such a lot of mathematics. We have done starting with the wave equations. See, all these wave equations and we have derived it. And so much of mathematics we have done just to arrive at the solution of Fc. See, the moment once you understand the concept, see how simple it is. So sometimes compared to the mathematics, the understanding is going to make the problem simpler. Is it clear right now?
Yes, sir.
Yeah.
Yes.
So the conclusion is, when I say the first mode, you can expect it that only one complete half cycle is present between the two plates. So that gives the corresponding cutoff wavelength for the first mode. Okay. Similarly, when you take about second mode, there are two complete half cycles are there. That defines the cutoff wavelength for the second mode and so on. And when you see the group of frequencies, the frequencies from FC1 to 2FC1, you can call it as the first mode. And what is that FC1 represents? FC1 is a cutoff frequency by assuming M is equal to 1. Okay. And the group of frequencies from 2FC1 to 3FC1, you can call it as a second mode. And 3FC1 to 4FC1, you can call it as a third mode and so on. Okay. Next thing is we'll discuss about the different type of waves: transverse electric, transverse magnetic, and transverse electromagnetic. See here, actually I have this is in this presentation I have given an approach how to the equation for TE, TM, and TEM. Just let us go through it once again. So in order to find out the equation for electric field and magnetic field, so first let me assume that in a waveguide, I will have the electric field something like this: Ex Ax cap plus Ey Ay cap plus Ez Az cap. And similarly, I will have my magnetic field intensity something like this: Hx Ax cap, Hy Ay cap plus Hz Az cap. So I was assuming that electric field consists of three components and magnetic field consists of three components. So forget about what type of wave it is. Okay. Now, in the parallel plate waveguide, what is the assumption we have done right now? The wave is going to propagate in which direction? If we see the parallel plate waveguide, what is the axis waveguide you have considered? That is the Z direction. Now, what we will try to do, I will try to express the transverse component. Transverse component means perpendicular component. Remember. So when the wave is propagating in the Z direction, what is your transverse component becomes X and Y. Longitudinal component is going to become Z. Have you got the difference? Transverse component means which are perpendicular to the direction of propagation. So when the wave is assumed to be propagate in Z direction, transverse components will be X and Y. And the longitudinal component is along the axis. So that is your Z direction. So what I will try to do, I will express Ex and Ey, which are the transverse component, and Hx and Hy is a transverse component. So my goal is to express Ex, Hx, Ey, Hy in terms of longitudinal components. Ez and Hz. Then I will solve the differential equation. Then I will get an equation for all this X, Ey, Hx, Hy and all. So that is an approach. So just do that. Just have a look on this method, what I have done. I have started with the time varying Maxwell's equations. So when you go for the time varying Maxwell equation, you are having a curl of H is equal to the conduction current plus displacement current. And since there is free space present between the plates, you can ignore that the conduction current will be 0 because your sigma equal to 0. Similarly, using the Faraday's law, you can see the curl of E is equal to rate of change of flux with respect to. So when I start, what you will do? You are having electric field vector and magnetic field vector. So you take the curl of vector and equate it to dou t. Okay. So when you expand the curl, what you are going to get? You will get this as a vector, and this is also a vector. So when you equate the AX coefficient on both the sides, you will get this equation. When you get AY coefficient on both the sides, this. Similarly, AZ coefficient. So similarly, if you do on the right side also, expand this curl subjected to this electric field, you will get one X component, Y component, and Z component. So equate the X coefficient on both the sides, Y coefficient on both the sides, Z coefficient on both the sides. So total, how many equations you are having right now? 6 equations. And how many unknowns are there? 6. Ex, Ey, Ez, and Hx, Hy, Hz. So there are 6 equations are there and 6 unknowns are there. You can use one of your best technique, whatever you can study in your mathematics, or you can go in a practical way, and you can see these are the solutions you are going to get. And whereas when I was expanding in parallel plate waveguide, in the cold equation, I can assume dou by dou y is equal to 0 because there is no variation in y direction. So after solving the 6 equations, I can express all my transverse component in terms of the longitudinal components. Is it okay? But you need not remember for the gate point. Just I was telling you the approach how to do it. But what you require from the gate point is concerned was you need to understand what is actually TE, TM and TEM. And till now, gate has not, in gate exam, they haven't asked any question such that you have to remember all these equations and that. But just you should know the approach how you are doing. So after taking the Maxwell's equation, and after solving the Maxwell equation, I was getting the transverse component in terms of the longitudinal components. You need not to memorize it, but what you need to understand here was when I was going about a transverse electric wave, your actual direction of propagation is in Z direction. So what you need to understand here was transverse electric. The name itself indicates electric field will be perpendicular to the direction of propagation. So either it can be in X direction or it can be in Y direction. Or in other words, for a transverse electric wave, there is no component which lies in the direction of propagation. So I can say Ez equal to 0. So will you agree with my point? So when I say transverse electric wave, there is no electric field in the Z direction. Agree with my point? Yes or no?
Yes, sir.
Yeah. In other words, you can say electric field is perpendicular to Z. You can say simply it is Ez equal to 0. So when you equate Ez equal to 0, you have a look on this equation. Tell me which all the component becomes 0. Okay. Your Ez is 0 means your first equation Ex also becomes 0. Okay. Then what else? Your Hy becomes 0. Like which field is exists? You are having electric because X and Z and magnetic field lies in X and Z. So you will have electric field in Y component, magnetic field in X, and magnetic field in Z direction. So these are the 3 components which will exist for TE. So see here, after solving these equations, you are going to get an equation for EY, HX, and HZ. Before that, let me ask you a question. Have a look on this. You have seen in oblique incidence, the transverse electric is same as parallel polarized or perpendicular polarized. Is it an example of parallel polarized or perpendicularly polarized?
Perpendicular, sir.
Yeah, good. You can see here, because the actual direction of propagation, this is your intended direction, but actual direction of propagation is in the XZ plane. Your electric field is perpendicular to the XZ plane, so it is basically said to be the perpendicularly polarized. So whatever you study perpendicularly polarized, that is an example of the transverse electric wave. Okay. Anyhow, these equations you need not remember. After solving this equation, you are going to get. But I will tell you a simple shortcut. Forget about the magnitudes part. I will give you which variation will come. Either it is a sine or cosine. Once you see in the rectangular waveguide, then you can understand. Okay. Before that, let's see the transverse magnetic also. So in case of a transverse magnetic, Z will be equal to 0 because there is no magnetic field in the Z direction. So having said that, you can see this equation. When Hz equal to 0, your Hx is also equal to 0 and Ey also become equal to 0. So you will have a magnetic field of Y component and electric field of X component. Okay. Yeah, you can see here that is the same thing. You will get a magnetic field in Y direction and electric field in X and Z direction. Okay. So these are the equations again when you solve you will get, but not required to memorize anything and all. So at this point, what you have to clearly understand was when you go for the transverse electric and when you go for the transverse magnetic, what all the components are going to exist. So this is very important, you have to remember. So in case of a transverse electric, you will have electric Y direction, magnetic in X and Z. This component you have to memorize. That's it, finally. And when it sees in transverse magnetic, your magnetic field lies in Y direction and your electric field lies in X and Z direction. This is the only point you can remember. Remaining rest of the things and all mathematics, it is required if you want to go for other things, but for the gate, it is not required.
But we took initially like nothing is there in Y, but again.
No. I have assumed it as dou by dou y is 0.
Okay.
Okay. But if you see the expand, you can see here ax, ay, az, and dou by dou x, dou by dou y is 0, dou by dou z is there. And third term is ex, ey, ez. Agree? Ey component is existing, but
Okay.
rate of change in y direction is 0, I have assumed. Yeah. Okay. This is how the transverse electric and magnetic waves look like. And first we will go to the rectangular waveguides then I will tell you the shortcut, which component will come under. And one more thing here, there is a concept called the dominant mode. What is the dominant mode means? As I said, any TE or TM is represented with a subscripts. In the parallel plate wave, anyhow, that is 0. N is 0. So what is the dominant mode says? The minimum value of M, which at least one electric field component and one magnetic field component should exist. So what should be the minimum value of M for which you should have one electric field and one magnetic field? That is basically said to be the dominant mode. Okay, now have a look on the equations. Have a look on this equation. Tell me what is the minimum value of M here in TE. So anyhow, second mode is N is 0. Okay, you have a look on these equations. When you put M is equal to 0, does it have any meaning? Does it have any meaning if you put M equal to 0? When you put M is equal to 0, all the components are going to vanish, right? So there is no electric field and there is no magnetic field. So I cannot say TE00 is the mode. Or otherwise, I already told you, when the second subscript is 0, and even if the first subscript is also 0, there is no electric field, which has no meaning at all. So what should be the minimum value of M right now? 1. So in case of a TE, the dominant mode is said to be TE10. So when you put M is equal to 1, all the components are existing. Our requirement was at least one electric field and one magnetic field. So that criteria is going to fulfill here. So the dominant mode in TE is said to be TE10. Okay, this is by assuming that you kept the plates in X direction. What will happen if you keep the plates in Y direction? Reply. What is the answer if you keep the plates in Y direction? Which is the dominant mode? 0, 0. Is it? Same thing. When you keep the plate in Y direction, your X component will become 0. And in order to have Y component, you should have one value in the N value. It is just interchange. T is 0, 1.
Okay, means
Is
like
it clear?
so because these equations are like independent of y, that's why it was 0, 0.
Correct, correct. In this case, if you are suppose keeping the plates in Y direction, what you are going to get? Instead of X, you are going to get Y.
Oh, okay, okay.
So that time, what is the dominant mode? Your T is 0, 1 is said to be the dominant mode.
Okay, sir. M is always for x and
X,
n is for
correct.
y.
Exactly, correct. Correct. So the first subscript is for X dimension and second one is for the N dimension, Y dimension. So similarly, can you tell me what is the dominant mode for TM? TM also same thing, right? TM00 doesn't have any meaning to say specifically. So minimum value of M should be 1 only. But technically speaking, if you put M is equal to 0, have a look on this equation. You are going to get one electric field and one magnetic field. Verify. Substitute M is equal to 0. So when you put M is equal to 0, first one is vanishing. And what about second one? Existing. And the third one is also existing. So technically speaking, I can say it is satisfying the definition of dominant mode. Am I correct or not? Yes or no? Yeah. But you can call that wave is a TEM wave. Okay. So first, before that, I can say the dominant mode is TE10 and TM10 for transverse electric and transverse magnetic. But technically speaking, TM00 mode is also existing, which will result your electric field in X direction and magnetic field in Y direction. Okay. And if you see the equation, whatever I have earlier, right, TM00, replicating that, Ez equal to 0 and H equal to 0. Can I call this as a TEM wave or not? Transverse electromagnetic wave. Can I call this or not? Yeah. Electric field in X direction, magnetic field in Y direction, propagation in Z direction. So I can call this as a transverse electromagnetic wave. Though technically, as per the definition, TM00 mode is satisfying the dominant mode, but the TM00 mode can also be called as a transverse electromagnetic wave. Because your Ez equal to 0, which means there is no electric field in Z and there is no magnetic field in Z. So that is the reason why I can call it as a transverse electromagnetic wave. So to discriminate TM00, we have introduced a new wave called transverse electromagnetic wave. That's what we have seen in uniform plane wave also. Electric field X direction, magnetic field in Y, and the propagation in Z. Okay. So for the TEM wave, what is the condition you are getting? Electric field in X direction, magnetic field in Y direction, and the propagation in Z direction. So what is the wave angle right now? So since the wave is trying to propagate along the Z axis, see here, this is your waveguide, and the wave is trying to propagate along the Z axis. What is the thing you are going to get? The wave angle is going to be 0. Yes or no? What is the wave angle definition? The angle made by the wave with respect to the axis of the waveguide. Because your axis is also along the z direction and the wave is also trying to propagate along the direction, your wave angle is 0 degrees. Will you agree with my point or not? So when the wave angle is 0 degrees, typically you cannot design any waveguide. What is the reason? Because you have defined the wave angle is equal to fc by f technically. So since your wave angle is 0, you require the cutoff frequency should be 0 Hz. So for the TEM wave, your wave angle is 0 degrees. So which means you require a waveguide with a cutoff frequency 0 Hz. If you want to have a cutoff frequency 0 Hz, what should be of A? Infinity. So that is means what? The transverse electromagnetic wave cannot propagate in kind of parallel plate or rectangular waveguide because you cannot achieve the cutoff frequency 0 Hz with a normal waveguide. Yes or no? So you require a waveguide whose dimension is said to be infinity. Agree with my point? So the TEM wave cannot propagate in parallel plate and rectangular waveguide because you cannot achieve the cutoff frequency 0 Hz. Because you require a larger dimension which tends to infinity. I can consider that the free space is also a waveguide where the TEM wave can propagate. Why? Because when you assume the free space, you know the separation is infinity. I can assume there is one conducting plate at the uppermost and one conducting plate at the bottom line, where you can see the free space is having an infinite radius. We can assume the free space itself as a waveguide where you can propagate the transverse electromagnetic wave. Is my statement correct? We have seen in the wave propagation, uniform plane wave happily propagates in the free space. That is the reason because you can also consider the free space is a waveguide where the cutoff frequency is 0 Hz. Because the entire free space, if you take, your radius is going to be infinity. You will have a large separation. So you can assume that the TEM wave can propagate only in free space. So do you have any questions here? Yeah.
So the wave cannot enter in any other angle.
No. See here, the wave can enter basically depends upon whether it is in which direction it is getting to be propagated. Correct. So right now, let me clear you this point. In this example, the wave is trying to propagate along the z direction. Okay.
Yes.
Initially, the wave is trying to propagate along the z direction, and your axis is also along the z direction. As a result, what will happen? It requires a wave angle of 0 degrees. In other words, I will give an example. See what will happen. Your electric field is in x direction, right? And magnetic field in y direction. And propagation in z direction. Suppose forget about your propagation. And this is your parallel plate waveguide. What happens to the electric field when it is trying to enter? Is it trying to enter perpendicular to the plates or parallel to the plates?
Perpendicular.
Yeah. So when the electric field is trying to be perpendicular, what happened to the reflected component?
Perpendicular only.
Yeah, which means that it is oscillating here.
Yes, sir.
So you cannot advance the wave. See, the wave can propagate provided your electric field should propagate with distance and magnetic field also should propagate with distance.
Okay.
But what happens the moment once the wave is trying to launch inside, your electric field getting oscillating because
yes,
it is trying to enter perpendicular, so it got stuck there. So electric field is not moving at all. So
yes.
when electric field is not moving, you can assume that the propagation also cannot happen.
Oh, yes, sir.
Yeah. So that is a basic reason.
Okay.
Yeah.
Because electric field is perpendicular, magnetic field is also perpendicular.
Correct. Since your electric field is perpendicular, it is trying to oscillate, it cannot move.
Yes, sir. Got
So
it.
since it is not moving, you cannot expect that wave can propagate.
Okay. So for that, the requirement is theta is equal to 0.
Exactly. So since your electric field is perpendicular and magnetic field also in y direction, so your wave is trying to enter along the z axis. So your wave angle is 0 degrees. So that is another way of explanation I can give it. See, because in order to satisfy this condition, I can give two explanations, either in terms of wave angle or in terms of the electric field. Technically speaking, if the wave should not get oscillate, means you should have an infinite waveguide. Okay, so that cannot be possible. Yeah. Okay, we can stop here right now. So we'll continue our discussion in the next class. So in the next class, we'll start with the rectangular waveguides. So whatever the concepts we have discussed, like cutoff frequency, phase velocity, wave angle, all these things looks to be same even for the rectangular waveguide, except that the wave is trying to restrict in both the dimensions. Okay, so before the next class, I will share the presentation. You just go through that and if try to get all the concepts clear. And as per the mathematics part is concerned, you need not to worry about it here. Just understand the concepts. Don't go through the mathematics. These mathematics and all not required for your gate. Okay. But as I said, in case of transverse electric and magnetic, you should remember which components are present. You need not to memorize all these equations and all. This is not at all important. But the basic underlying principle you should understand. So when I say transverse electric, your Ez will be 0. Corresponding to that, which components are existing? Similarly, when I say transverse magnetic, there is no magnetic field in z direction. Correspondingly, which all the components are existing? That's it. So if you remember that points, it's more than enough. Okay. So we'll continue the same discussion in the next class, followed by the problems. So probably in the next class, we are going to complete the waveguides, full problems along with the theory. And there is one more last class I can dedicate only for the this one antenna part. So antenna will take 3 hours of the lecture for the gate. Okay then, do you have any questions to discuss? Yeah. Okay then, you can sign out.